So today we finished up our definitions and kind of set the stage for the analysis that we'll start with our next lecture on hydrostatic. The new definitions that we went through today was we defined Q, which is the discharge in channel flow. And the way we think of this is as a volume per time, meters cubed per second, for example. Think of it as an averaged velocity times area, or an integration of velocity, and we'll use that in our first laboratory. We also talked about pressure being the normal force per area, and we talked about the shear stress being the shear force per area. We frequently work with forces per volume, which many times become forces per area in fluid mechanics, and so pressure and shear stress become really fundamental quantities that we'll work with quite a bit when we work on the dynamics. We talked about the viscosity. The viscosity is the relationship between the shear stress and the velocity gradient. And so du dz is the velocity gradient. Shear stress, as we just said, is the shear force per area. And so this mu, this is a plus or minus up front here, mu is the viscosity. A velocity gradient in the interior of a fluid creates shear stresses within that fluid, dragging the fluid above or below along with the adjoining layers of fluid. And that's what this equation represents. So the relationship between velocity gradient and shear stress is a fundamental one that we will use throughout the semester, and the viscosity is simply the proportionality between those. The last two concepts that we introduced was the surface tension, for which the surface tension force is equal to a surface tension constant times a length. The surface tension parameter sigma is one that is tabulated for different fluids, and then the length depends on the geometry of the problem. And finally, the vapor pressure. The vapor pressure is the pressure at which fluid boils, and it is a strong function of temperature. And so we talked about when water boils, at 100 degrees C, it boils at atmospheric pressure. If pressure goes down, it boils at a lower temperature. And in fact, if pressure is reduced enough, it could boil at room temperature. And so that's the point where we introduced cavitation. So cavitation is the point where P is less than or equal to the vapor pressure, and then we get microbubbles forming in the fluid that can then damage equipment, damage pipes, and so on. So with that, we've really completed our sort of tour of terms and concepts that we need to understand to set the stage. That means in our next lecture, we could start talking about hydrostatics, which is going to focus on pressure in a fluid that's not moving. So for a few lectures, we don't let the fluid move, and we focus on how pressure varies as a first step towards understanding the dynamics of fluids.